Okay, thank you everyone for joining us today. We're going to get started so we can stay on schedule. We really appreciate you joining this third and final installment of our Prestressed Concrete Bridge Design Seminar. I'm Dawn Decker, Executive Director of PCI Mid-Atlantic, and this program has actually been brought to you by PCI Mid-Atlantic and PCI Northeast chapters of the Precast Prestressed Concrete Institute. I know you have a lot of questions about these items, our housekeeping items, so I'm going to cover off on these first thing. Please note that all attendees will remain muted throughout the program as we are a very sizable group. We do want to hear from you though via the chat function, and quite frankly, we have an exciting program built into today's seminar, which is a 40-minute roundtable panel discussion. So please submit your questions so our panel members can address those, and you can just use your chat function. We'll make those our primary starting content for that roundtable portion of our seminar. So many of you have already asked about handouts. So there will be two links provided in the chat function, a Dropbox link and a WeTransfer link with folders with numerous handouts, and they will cover off on all the materials that the speaker will cover. So whether one works for you or the other, we found that both you will be successful using one of those. We have also noted that we are recording these sessions because, as someone already mentioned, they may not have attended or been able to attend one of our two other previous sessions. We'll email you since you have already provided registration information and make sure that you have access to all the handouts, responses to the questions, and some of the other reference materials that will be located on our websites. PCI has met the standards and requirements of the Registered Continuing Education Program. Continuing education credit will be reported based upon your time of attendance in this seminar today. You will receive a link to download your certificate from RCEP. So please check in about 7 to 10 days for that email, and you should be able to download your certificate accordingly. Please note that sometimes this goes into your spam box. So if you do not receive an email, check your spam box to make sure that you have access to that information. Please know that permission from PCI is required to use any of the material that's delivered during this program, as it is copyright protected. And as the Executive Director for the PCI Mid-Atlantic Chapter, I provide technical and education support to DOTs, the design and construction community, and professors in their academic curriculum. And our chapter, the PCI Mid-Atlantic Chapter, covers New Jersey, Pennsylvania, Maryland, Delaware, Washington, D.C., and Virginia. New York City is an overlap area where Reid Castrodale and I cover that respective territory. So the Mid-Atlantic Chapter has 14 transportation producer members, and they are very willing and able to provide you design assistance, budget development, schedule planning, plant tours, value engineering assistance, and other services to state DOTs and their engineering consultant partners. It is an absolute privilege to introduce Reid Castrodale and the rest of our presenters for today. For the past 30 years, Rita has provided leadership, support, and education to the New York City market, where we both work jointly, as well as to the rest of the state of New York, Connecticut, Rhode Island, Massachusetts, New Hampshire, Vermont, and Maine. Through Rita's Bridge Technical Committee, countless resources, which Mike Culmo will talk about some of those, an update to next week's guidelines. New products and training seminars like today's seminar have been delivered in partnership with state DOTs in her marketplace and regional producers. It is my privilege to introduce Reid Castrodale, who is the president of Castrodale Engineering Consultants. He provides consulting services specializing in prestressed concrete, lightweight concrete, and accelerated bridge construction. He is a registered professional engineer in 3 states. Reid is the bridge consultant for our Georgia Carolinas PCI chapter, the managing technical editor of Aspire magazine, which Rita will mention in the next session, and a fellow of PCI. He's been active in various PCI bridge committees for over 30 years. JP Binard is the owner of Precast Systems Engineering, which specializes in construction engineering primarily focused on precast, prestressed concrete for buildings, marine structures, and bridges, while utilizing ultra-high performance concrete in components and connections where possible. And JP actually will be speaking about this topic with us today. JP chairs various PCI committees as well and has authored and co-authored several papers on ultra-high performance concrete and precast, prestressed, other topics as well. Mike Culmo is Chief Bridge Engineer for CHA Consulting, Inc., and he is a structural engineer with 37 years of experience in bridge and highway design. He has extensive experience in the design of steel, concrete, and prestressed precast concrete bridges, and has been responsible for managing design teams on new expressway bridges, highway interchanges, bridge rehabilitation, and related highway structures. He is a licensed professional engineer in 8 states and the author of numerous national publications and manuals on bridges, and was a principal author of the 2018 Astro Lrft guide specifications for ABC. On our panelist discussion, our roundtable today, we have 3 fabricators from our 14 respective state area. From left to right, we have Russell Dixon. He is the VP of Engineering at Prestressed in Roaring Spring, Pennsylvania. Troy Jenkins is the VP Chief Engineer of Northeast Prestressed Products in Cressona, PA. And Mike Wigan is the Chief Engineer of JP Carrera and Sons in Middlebury, Vermont. I'm sure we'll have a very robust discussion. And as I mentioned, please make your questions in the chat function for our panelists, which will include also Reid, JP, and Mike. We have a couple of handouts that I'll reference now very briefly, and Rita will speak more specifically to one of these in a little bit more detail. PCI Mid-Atlantic and PCI Northeast, you see these pictured on the slide here. There is one each for each of our chapters, our transportation producer member product directories. So on this, you will have contact information, the name of the companies, as well as the respective products that they produce. Those products are grouped into bridge products, piling, precast substructures, and miscellaneous transportation products. Please use those, download those, and contact the producer members for a variety of services, which Rita will talk a little bit more about as well. And in terms of education opportunities as well as publications, Rita will speak to this handout, which is PCI recently published a new 2021 Transportation Publications and Online Resources Catalog. So Rita will speak more specifically to these publications as well as the on-demand learning courses that are available for you on a wide array of subjects. Now, getting started in terms of our program today, Rita Castrodale will start us off with a review of the PCI Body of Knowledge. Following that, Reid Castrodale will cover lateral stability. JP will have back-to-back sessions with girder repairs and fabrication issues, as well as UHPC for bridge elements. And Mike Culmo will review next beam guideline updates. JP, Mike, and Reid will facilitate our fabricator panel discussion. And again, please submit your questions so that we can address those during that panelist live discussion. And finally, as a reminder, I just want to let you know again, for those of you that may have just joined us momentarily, the continuing education credit will be reported based upon your time of attendance in the seminar. So you will have an opportunity in 7 to 10 days, get an email and download that certificate from them. Now I'm going to turn it over to Rita, who is going to talk with us about the PCI Body of Knowledge. Thank you for joining us.
Show screen.
Okay. And again, good morning, and thank you for joining us today.
All right, we're getting the screen going here.
This takes a couple of minutes.
Okay, I think we're set to go. Good morning, everyone. I do apologize for those that were good enough in making session 1 and session 2 already, but I do want to go over the resources for a third time in case we do have some new people here today that didn't get the opportunity to hear about our resources, and a quick update on PCI Northeast Technical Committee. So again, I'll try to go through this relatively quick. So for those that have already heard this, it will be brief. So the thing that I want to really call everybody's attention to again is the brand new Transportation Publications Catalog. It was just completed about a month ago by PCI National. And the value of the resource is that it has anything related to bridge and infrastructure and kind of a one-stop shopping. So to get to it, you want to go to pcine.org. You want to look under design, then transportation engineering. You will see the document listed there. You would download the catalog. If you are online, this document is interactive. You will be able to be actually getting links directly to some of the resources. When you open it, you will find a complete table of contents of what is in it. The first portion of the document is all our publications related to transportation. And then the second part of the table of contents is all the educational resources that are available. So visually, this is what it's going to look like. When you open it up, it lists the actual publication. It will list a brief description of what is in that publication. And in the light blue area on the right-hand side, if you click that, it will bring you directly to the bookstore where the publication lives, and you will be able to download it as an electronic copy. And you will find most of these are free. There are some of them that you would have to pay for, but you will find most of them will actually be a free electronic version. If you are interested in a hard copy of that document, you would have to purchase it from the bookstore. So again, it's only the electronic version that would actually be free. And the thing that's most important here, I do want to call out, is the PCI bridge design manual is there. So if you are working on a prestressed concrete bridge, that would be the document you would actually want to download. So if you can't find the actual transportation resource catalog and you just happen to go right to the PCI bookstore, I do want to show you that you can get there in the same manner and download some of these same documents. So if you actually go to pci.org or PCI or PCIMA, any of the PCI.org organizations, you'll click on the publications tab. That will open up to bookstore and periodicals. I do want to note, we do have 3 publications. We have the Ascent, the Aspire, and the PCI Journal. The PCI Journal is a technical publication. The Aspire is really our industry magazine related to transportation. Aspire is actually free. You can view all of the documents, all the past publications for it on the website, and read anything that's current there too. PCI is always looking for projects to feature. If you do have a nice project that is a bridge project that you would like to potentially get some PR, you would want to contact Reid Castrodale. He actually would be more than delighted to work with you and potentially getting a story into that document. So moving back to the bookstore, if you click on the bookstore, and it will bring you to a page that looks like this. You would click on transportation infrastructure. It will filter all the publications related to that topic. Sorry about that. It jumped on me. Yeah. There we go. So there's the bridge design manual, and you can filter these and you can see all the publications that are available. And again, if you click on it, it'll bring you to a page where you need to register to download it for free. So now let's move over to the other section of the resource guide catalog, which is really a listing of all PCI's educational resources related to bridge. And it's under the e-learning center. So when you go there, what you'll find in the catalog is a description of each of the classes. And again, you will be able to link directly to that particular class if you're interested in taking it. And this is just, it gives you an outline of what's physically as far as there. The T100 series, as an example, covers chapters 1 through 9 of the PCI Bridge Design Manual. The T200 series covers full deck precast deck panels and so forth and so on. You will get a feel for some of the topics that are covering when you click on those. All of these were written by a team of experts. They provide theory, design steps, and information related to precast, prestressed concrete bridge products. I'm noticing my thing won't go forward because we keep getting people trying to get into the class. It's locking the screen up. Again, you can get to that document through, not the document, through the e-learning center, through the education tab. And I do want to note on the education tab, there is also other bits of information available to you. We have monthly webinars. They're free and on demand. There's the PCI Academy, which is actually a free and it's a fee-based class that you can take. It's a live class. And then there's the e-learning center, which I'm going to go through here in a minute. And then finally, we also do offer live and virtual learn and lunch programs. So if you do want Dawn or I to visit, please feel free to reach out to us, and we would be delighted to schedule a program for your office. So going into the actual e-learning center, this is what it looks like. You can filter the transportation courses. There are also building courses there, so it's not just transportation. If you click on transportation, it will filter all those courses, and then you can sort them in alphabetical order. And so the T100 courses would sort to the first level. I do want to make one quick note before I go to the next slide. If you do click on the technical resources, there are two schools there that were actually part of the PCI Academy. They are actually not live. They've been recorded. So if somebody is new to prestressed concrete, has not taken a prestressed concrete class at a university and want to learn the basics of prestress before you dive into the actual bridge class, there is a 6-module, 90-minute each class that's free. You can go in and listen to it. It was pre-recorded by a professor actually was presenting it. So it would be a good opportunity to learn the basics. We also do have an advanced version of that, but that actually is a fee-based class. So this is what it will look like when you sort it. So there's the T100. Again, these are all the basics if you're trying to really learn prestressed concrete bridge design from the beginnings, from preliminary design to materials to design loads, flexure for service limit state, and so forth and so on. So it's a very good resource, and you will basically be able to really get a good hands-on feeling for designing a prestressed concrete bridge. This is what once you've picked a class, you do need to register, you log in. And then once you log in, you will be able to start the class. This is what the module actually looks like. It's approximately 60 minutes long. It's self-paced. It's a talking module, so you can play it back if something is not clear, and then you can move forward. There are tests along the way, and there is a final test at the end in order to get PDH credit. So if you are looking for credit, you do need to take the tests. And then you can download the PowerPoint notes so that you can follow along with the presenter. Quickly, I want to talk briefly on the PCI Northeast Bridge Technical Committee. Quick update, Mike Culmo will be presenting a little bit later on today, and he'll go through the next beam guidelines. This is the matrix of our committee. Our committee is 30 years old. It's hard to believe it's been 30 years since we launched this committee. It's made up of all the DOTs in the New England, New York area. We have consultants, we have precasters. It's a partnership we've been running now all these years, developing technical documents that we use up in the Northeast corridor. And here's the picture of the first Northeast bulk T that was developed back in 1995. And you could see Reid Castrodale in the picture because he participated in the helping of the development of that beam. So what's new? The next beam guidelines are brand new. We just posted them. We're calling it the second edition. Mike will go through the details of what's changed. For those that have been using that document, you will be able to learn what's different. The next document I want to note that's relatively new is the full depth deck panel guideline. We posted that last May, It's got a lot more information. I'll go through a couple of things that we changed in that document just to bring you up to speed. And then the other documents that are available are the Stay in Place Deck Panel Guideline, the Northeast Deck Bolt T Guideline, which we developed back in 2018. We have a Camber and Profile Management for Adjacent Members document that was published in 2018. And then finally, the Resolution of Nonconformances in Prestressed Concrete Bridge Elements that was posted in 2018. The current work of the committee, we are currently updating the Accelerated Bridge Construction Guidelines. Usually once it's in committee, it does take some time. We are kind of doing a major rewrite of this document. Nothing wrong with the current document. I do want to note that, but we're changing the format, adding new ABC details. We're hoping to finish it by the end of this year. We'll see. One final note, all the documents I'm mentioning here will be on PCINE.org. You will not find them at any of the other websites. So you do need to go to PCINE if you are interested in any of them. And then finally, I do want to note that if you are looking for help, which is a common question, you know, need budget development for a project, I need schedule, I need to know whether, you know, especially if it's an ABC project. I would encourage you to reach out to a PCI certified plant in your area. They can help with that. The regional associations can't help with cost data, since that is something that we just don't have access to. Also, if you are outside our region, the Mid-Atlantic and the Northeast region, I know we do have a lot of people that are out beyond this area. You can find all the regional associations listed under the regional tab. And I would encourage you, if you do have questions in your region on ABC or any other topic related to bridge, I would reach out to the regional director in that area. And I think that's my last slide. So we are now going to launch with, I will stop sharing, and I think we move on to Reid.
Well, thank you, Rita. I appreciate that. Hopefully everybody can see my screen now. It's good to be here, and Rita didn't mention that her picture, as well as Mike Culmo's picture, and I don't know if anybody else that's on the call today are also in that photograph that she showed, but there are others who were involved with that girder who are still kicking around here. Well, what I'm going to be talking about is lateral stability. And it's a topic that we're seeing a good bit of. What we're talking about is that stability can be an issue for long girders, but one thing to bear in mind is that long is really a relative term. It really is an issue of the slenderness and the lateral stability rather than just the length. So that's something to bear in mind, but typically we think of stability becoming an issue as we stretch out our girders, as we're able to do now with high strength concrete and 6/10 strands. I did want to point out one other item that's a possibility for affecting stability, and that is the site access. And I was just reminded of this the other day when I was preparing for this. This is a picture of some spliced girders, or one of the spliced girders that was going into the Shelby Creek Bridge in Kentucky, built in the early 90s. And they had done some evaluation as they were going in, and there were issues with significant cross slopes. This is up in the mountains of eastern Kentucky. And the grade getting in from coming down from up here and around and getting down to the bottom here, that was up to 14%. They actually hooked a bulldozer onto the trucks to keep them from getting away as they were descending into the bottom of this site. So they, as you can see here, put a truss on the top flange, and they also added some strands in the top of the girder. And there's a good discussion on that. So if you want to just take a look at it for interest's sake, but this was back before we started a lot of our discussions on lateral stability, but these designers took it into account as they were working on this design, which is a good example for all of us. PCI has recently published a recommended practice for lateral stability. And there's also a spreadsheet that's been developed that executes the equations, the calculations that are gone over in that recommended practice. So there's now the spreadsheet and an instruction manual. And actually what you do is you download the manual and then you get a link for downloading the spreadsheet. So those are available on the PCI resources that Rita went through just now. There's actually even already been an errata for the recommended practice, and an update on the recommended practice is underway, but it'll probably be a year or two before it gets completed. One thing I would recommend is, as Rita was talking about, you can get the e-learning courses on lateral stability, and there are 4 of them. They're in the 520 series. You can get those on the e-learning center on PCI. So I can only hit a real high level discussion this morning, but you can get it much greater depth if you take those series of courses, which again are free. Now, there are a number of approaches that can be used once we design a girder, or as we are designing a girder, to improve the stability for handling an erection. And we're going to talk about a couple of those now. One of the major ones is that we can move the lifting loops in from the ends. And also this temporary supports either for trucking or for dunnage during storage. You need to move those in and you'll improve the stability significantly. However, we have to check the stresses. If we're lifting from further in, then we now have a cantilever at the end, which gives us some negative moment at the lifting points, and the stresses are not usually checked there when we're doing a design. So I would encourage you all to take a look at that. Some DOTs also have a maximum distance to the lifting loops indicated either in the standard beam sheets or in the specs, and we need to be careful about that. The lifting at about 1.5 times the depth of the girder in from the end is a good rule of thumb. But if it's specified as a distance from the end, like 3 feet, it can lead to problems. Years ago, there was a story told probably 20 or 30 years ago up in Minnesota where one supplier had been fabricating girders for a good while, and they knew that they needed to move the lifting points in from the end. Then a new fabricator came in, the specs said lift them at 3 feet or whatever from the ends. So they picked this long girder up from the ends and it rolled over. And they said, okay, DOT, that's your girder. We built it like you told us to. So we have to be cognizant that there are factors now as we're looking at these long beams that we have to take into account in our designs. One of the things that's done is that to increase the stability for transport is that you move the bunk points in for transporting the girders as well. You can see that there are overhangs here. The bunk point's pretty far from the end of the girder here. And that's usually the same thing at the front and the back. They may be different. Another thing that is always assumed is that the girder is rigidly attached to those trucks. So we need to just be sure, and that's something that's in means and methods for the fabricator, just to be sure that those attachments to the truck are indeed pretty rigid, good stiff connection. One thing that we can also do is to raise the center of rotation above the top of the beam. The standard strand loops, which you can see here on this girder, those strand loops provide a point of rotation that's just at the top of the girder. It's not at the top of the loop, it's at the top of the girder because those strands can bend over. It turns out if you raise, using a rigid device, if you raise that point of rotation above the top of the beam, then you get a longer resisting moment arm. So that improves significantly the lateral stability. And there are a number of approaches you can see here with rigid links coming up through the top flange, like here and here. There's some things that are attached on the outside. And you can also use a sling. Now, a sling itself is not rigid, but when you put it in this configuration, it does become rigid and can be used to improve the stability of a girder. In some cases, exterior frames are applied. This one right here is the Shelby Creek Bridge that I mentioned earlier. They had a nearly full length frame attached. Here are some other frames that have been attached to these girders to improve their stiffness, to improve the lateral stability. It's not always required. In fact, it can, in most cases, be taken care of now that we have wider top flanges on our beams. In design, we can also add top strands to the top flange, or add strands to the top flange, and they can improve stability because it makes the top flange less likely to crack, which is when you lose stiffness and then lose stability. It improves the stresses for lifting if you're moving in the lift points, but it does affect some designs. I discussed this in a previous presentation in this webinar series. In most states, designers aren't given the responsibility to consider conditions other than transfer and final conditions on bearings. So that's all that we have in the past typically designed for. However, that's not what we really need to take a look at. Some pre-stressors have had the experience that they receive a girder designed, and as the girder was designed and bid, it really cannot be safely handled and or transported. And in that case, the design has to be modified to address either the high stresses or the lateral stability issues. But typically what's done is moving the lift loops in, but as you move the lift loops in to improve the stability, then you exceed stress limits when you're lifting it, and a design modification is required, or adding reinforcement or other strands, whatever it might be. And anytime you have a design modification after bid, that causes delays and increased costs. So we need to consider that. And what's being encouraged now in the specifications is that we consider stability. Here we can see some text out of the Lrft specs. This is the 9th edition, 2020 version. The first item that it does is it speaks about adding stability for what shall be investigated. This is 5543 on stability in the specs. And the words "and stability" were added back probably 4 or 5 years ago. In addition to that, the commentary alerts the designers that handling, transportation, and erection can govern the design. But if we consider it as designers, it doesn't make the designer responsible for the contractor's means and methods. And then also this commentary does give references, the recommended practice from PCI, and also a detailed design example. So that's good to be aware of this information that's now in the specifications. Here is another section on precast beams. And you can see here, and this has been there for some time, I believe, this text has, that the pre-service conditions are the responsibility of the contractor. However, this has been added. The pre-service conditions may govern and should be considered in design. So we need to be aware of that as designers now. Also, there's some text in section 5 or article 5511, and this is on the specification side. And this text has been in the Lrft since 1994 when it was introduced. It says that stresses and deformations for critical stages during construction, stressing, handling, transportation, and erection have to be considered. So that puts us on the hook to consider them. We aren't responsible for getting it there and making sure that it can be erected safely, but we need to consider that. But how do we know what to do? You know, how do we know where the girder needs to be lifted? How do we know what kind of transportation is going to be provided and all that sort of thing? Well, we have a couple of good examples of some approaches to handling this. WashDOT, Washington State DOT, has developed a great approach. They've developed this over a number of years, so it's been tested out. They've shaken the bugs out of it. they do not want fabricators to change a design in order to make it work. They want a girder that when it's bid, it can be fabricated using that design. So they don't want designers to have, or fabricators to have to go fiddle with the strand pattern, move lifting loops, all that sort of thing. So all of that is considered in the design. The designers check those using parameters that are provided by WashDOT in both the specs and the bridge design manual. And so that way the designers can handle it. Their design software that they use up there also includes all of that information. It has gotten a little more complicated because they've gotten some new transportation equipment. There's an approach that they've come up with how to deal with that. There are a number of good references. I'd highly recommend anybody that's wanting to be proactive and do some lateral stability analysis to check these WashDOT references. There's a PCI journal article, there's an Aspire article, both are excellent. Then, as I mentioned, the bridge manual and their standard specs both address lateral stability and provide information needed for the evaluation. And then there was a great presentation that Rick Bryce gave from WashDOT, gave to the Georgia Carolinas PCI meeting back in August a year ago. And there's a PDF of that presentation, as well as all of the supporting information, including the bridge manual and standard specs sections. So you can pick that up at the reference provided there. South Carolina DOT, of course, this is down in my region, but South Carolina DOT states things this way, where they give the designer a responsibility for preliminary investigation of the stability and shipping issues. But right after that, they say the contractor is still responsible for taking a look at it. So that he remains responsible for getting the girder there and erected successfully. But the preliminary evaluation is essentially like an erection plan. You are making sure that that girder, based on some assumptions that you're making, can be successfully fabricated, transported, lifted, and handled, all that sort of thing. So it's essentially like an erection plan from that, as far as how it's handled responsibility wise. One other example is from Georgia DOT. They actually have a table that's in their bridge manual that provides maximum beam lengths for each of the girder types that they use. And those maximums are set based on stability considerations and also an assumed distance in from the ends for lifting loops. Designers can use designs that are greater than that, but then they have to do a stability analysis. So in summary, we're starting to use longer spans. Lateral stability may become an issue, and also stresses can be exceeded, and in some cases, design modifications are required for girders that are received as designed. But now we have some good information. There's some new information and requirements in the Lrft specs that have helped out and defined better the responsibility of the designers. And then PCI has developed some excellent resources as well. So I would encourage owners as well as designers to consider implementing these new requirements. And with that, I am done with lateral stability. If you have questions, be sure to put them in the chat box. We'll see what we can do about answering those. And now it is time to pass the microphone and screen over to JP Binard. Thank you very much.
Thanks, Reid, so much. Sorry, the share screen was in the way of my slideshow. So we'll start here from the beginning. Hope you all can see my screen. So I'm going to talk to you guys about girder repair and fabrication issues, some of the common things that come up in the plant, as well as some resources you can use. Certainly, this is an extensive topic, but we'll start it from kind of a broad-based approach here. Thanks to Don's introduction. So Precast Systems Engineering is the name of my company. I started in 2016. I was a former chief engineer of a precaster in Southern Virginia. And I'm partnered with Precast Systems Incorporated in Trenton, New Jersey, as well as Core Tough Uhpc, which I'll be talking about after this presentation. So what is the goal that we're all involved here, regardless of the material type, is to build a bridge, right? And so concrete offers a very unique opportunity to come up with custom shapes, custom designs, and custom span lengths, and we, as Reid has mentioned over the past 2 sessions, there's been a lot of work done to make this repetitive, to make it easy. But sometimes things don't go necessarily according to plan. And as concrete is so variable in the different types and shapes we can have, sometimes we're left with incidences that may be unique to the material. So this is a kind of a funny story. We had made 3 products. We had a couple problems with the first 2 products. The 3rd product was perfect, and a crane brake, actually a small air hose and a crane brake failed, and the spreader beam dropped on the existing conforming product. So what do you do then? Got a nice pile, it's in the yard, guy backs up with a forklift, a small spall. So what do? Transporting can always create some problems, as Reid mentioned, for lateral stability. This is an MOT issue, perhaps, maybe not laying out the turn well enough. And then this is an extreme event. It's just shared from NPP at Troy. I find this this slide to be very indicative of the worst things that can go wrong. So when we're in the fabrication facility, we need to make a game time decision, right? We have something that may not be conforming. We don't know what to do, but we have to decide quickly. So there's lots of things that we have to take into consideration, right? Is the repair best before detentioning, or can we do it in storage? How will the damage affect the girder? What repairs prior to detention will be pre-compressed? We want to keep that section elastic, right? Keep it pre-compressed. And if you do an odd bed repair, so as Reid had mentioned, the cycle time and things that come into play for fabrication, you can't necessarily hold up the production to wait for an approved procedure. So these answers are always needed fast, and they have to be quickly executed. And so this is really why back in before 2006, but when it was published, the PCI M&O 137 was created. It's the Manual for Evaluation and Repair of Precast Prestressed Concrete Bridge Products. A group of owners, designers, producers, and consultants all came together, as well as university, came together to kind of look at what are the common things that occur at a plant and what are the reasonable things that can be expected for the plant to administer under the QA/QC plan. Oh, I meant to mention as well, sorry, that Northeast, as Rita had pointed, they've updated this manual in 2018. So PCI Northeast has a more broad product base where they've expanded it to like deck slabs, for example, and substructure units. So I greatly encourage you to look at that resource as well, which the link is included from the Dropbox. Currently, PCI M&O 137 is undergoing revision and will include a lot of those things that are in the Northeast publication. And the layouts are similar between the 2 documents. So, there's an introduction, there's troubleshooting, standard repair procedures to keep in mind, methods of patching, epoxy injection for cracks, and then the references that are available. It's broken down into causes, prevention, engineering effects, and repair considerations. So here's the general layout of the manual. If you're not familiar with it, I strongly suggest that you download it from the PCI website. It's a tremendous resource, even though it was published in 2006 and being updated. A lot of the information will be untouched and preserved. So you can see there's causes. For example, this was a honeycomb or void, whether it be a pile or a girder. At the end of the pile or girder, you can have a honeycomb or void, or in the web. And so there's a causes. So it could be vibration, it could be bleed, the method of placement, it could be the concrete mix, and it could be the design details. Maybe it's overly congested at that location. So the prevention is also included side by side. So it could be, you know, provide better internal or external vibration. External vibration takes place on the forms. Adjust the concrete mix. Lots of folks that move to SCC for these kinds of reasons. Or improve the details, reduce the congestion, perhaps do away with some of the splicing, like Reid had mentioned, I believe, in the first session. And avoid the use of horizontal reinforcement. Sometimes that can cause the concrete to hang up. It talks about the engineering effects. How will that honeycomb or void affect the product, if it's in the bearing area, for example. And then the various repair considerations. So this is somewhat dovetailed, if you will, with a kind of a troubleshoot item and then a standard repair procedure that's corresponding to that element. So, you know, as you can see on the left there, these are cracks, okay? So there's a whole section on cracks and then a standard repair procedure. So perhaps you have detentioning cracks, it can be design related and the cause relation and prevention, and then goes into the types of repairs that you can make. So oftentimes, if there are detentioning cracks, they're near the end of the beams, those can be silane sealed. If they're below a certain threshold, then the deck usually compresses them anyway in service. And so that's commonly how we handle those. You know, local cracks like this, or even in the spalls and the corner cracks. So all this is highlighted inside this document, and different types of repairs are discussed. What items are not currently in that manual is really what we've been focused on in the Bridge Producer Committee for PCI. So sweep, for example, is one. Camber and camber variability. There's some bars missing as a common problem. And then full depth deck panels. And as I mentioned, PCI Northeast publication, they show substructure elements, unique products that we're producing more and more in these two regions that are not necessarily addressed directly in this manual and are very important. I'll also note that we're going to include a section on the materials that are used, the service life performance. There's been a couple publications about at least patching materials and the key components to those patching materials in order to end up with a serviceable repair. So it should be noted that, you know, this manual, this resource, the knowledge base that produced this manual originally, it has been used and been in service for several decades now, so or almost two. So, or the concepts that were there were long utilized before, but now they've been adopted nationally instead of regionally. And so that's really, you end up with serviceable, durable repairs because they're currently proven by empiricism. So sweep can be a major issue for lateral stability, as Reid mentioned. It can be a major issue for fit up. It can be, and as we continue to extend our spans, you know, that number starts to get larger each time, and so we're working on understanding the phenomenon better. There are two excellent articles that are published in Aspire on this subject. And so we've taken that information and, I'm sorry, 3 excellent articles that are published by Inspire. So we're trying to take that information and expand it. So this is sort of a unpublished first draft that we've worked through in the Bridge Producer Committee. And so what are some of the reasons, the causes for sweep? So you might say potentially misalignment prior to casting. You could have incorrect placement of strands. So you can actually put some eccentricity on your product, and that could result in a sweep after casting. Lifting and storing, sometimes, oftentimes, for producers, not all producers, some store on concrete or well-graded material, but sometimes the dunnage may not be level or true. A lot of our dunnage is hardwood dunnage, and sometimes that can result in really setting the girder and creating almost a situation where you're inducing creep. And I'll get to the prevention or the solution next. And also in the field, sometimes you can have a slope bearing in the field, and so you can get a measurement of sweep that may not be accurate. So, so some of the preventions, obviously, ensure your formwork is level and secure. That's always within the purview of the producer and the QA process, the QC process. Make sure your strands are within tolerance. If a whole group of straight strands are off by a certain dimension, yes, that can create an issue. And so you You can always provide chairs. You can check your anchorages to help to mediate that. Lifting and storing, I think one of the things you can do is actually when you check the sweep, you find it early on in storage, you can shift the dunnage to go the other way, and it will actually the sweep, if you will creep out and balance itself. So a lot of us producers know those tricks. And then in the field, you can pick it up and rotate the girder, assuming it's symmetrical, and that can, or pick it up and rotate the bearing 180 degrees. Both are accurate, and that will allow you to see whether or not that bearing had slipped or slided, or if there's an as-built condition of the bearing. And of course, we're open to, this is still unpublished, so we're open to any of your comments or feedback on this issue. This is a national publication, and so we have a lot of producers that are engaged in this conversation, as well as the designers, university, and owners. So I blew it up the second slide. Sorry, that's what we just went over. The next one is Camber. So Camber is always a hot topic for producers and for owners alike. It's not always obvious how to deal with Camber after it happens, right? So and note that this Camber seems excessive, although this is from Washington State, and these actually had Camber built into them. So don't be misled by that span to depth ratio in the Camber. So Camber 2, we're trying to kind of find what is the real causes and prevention methods. From a producer standpoint, when a design is created, really we're fabricating products, and those products result in the camber that's imparted by the pre-stress force, right? There's a few things that occur. We might have, for example, various curing durations. That is just a function of cycle. But there's also tolerances, right? So there's always tolerances to these products. PCI MNL 135 is a tolerance manual. PCI MNL 116 is really our QC QA manual, and all of these are available through the resource guide that Rita mentioned in the beginning. And so they give tolerances to each product. So you might have a tolerance in your web width, you might have a tolerance in your height, you might have a tolerance in your flange. Your top flange especially might have various heights due to the rake finish. And so these can play a minor role, but as the sum can play a major role in some of the resulting dimensions. The pre-stress force, your allowed elongation tolerance, and then obviously if there's an error, then that can be. Camber is also a great tool, right? It's as some folks have said, it's kind of like taking your blood pressure. It tells you, a general range of where you are and what your product quality is like. So materials also vary because your strength can vary, modulus elasticity can vary, your unit weights, and you never want to measure. You might have solar effects with measuring, and then we talk about all these things. So I encourage you to review this. We'd love to hear some feedback. Generally speaking, a bridge meeting that talks about camber tends to last too long. So I don't want to beat the horse here. The roundtable may pick this up as well to talk about some of the ways that we mitigate camber issues. And as Rita had said again, she has a great resource on this topic. So we talk about repair considerations. Really, one of the simplest repairs, which actually Reid brought up years ago, is to adjust your bearing seat elevations. A lot of bearing seat elevations are cast in place. So if you recognize an issue where you're getting excessive camber early on, and you haven't poured those bearing seat elevations yet, then you can simply lower those seats based on the as-built information. So that's where collaboration, going back to my first slide, is so important in building this bridge, because a higher camber is not necessarily indicative of a poor quality product, right? So it just takes communication. So this is an issue that's come up more and more in the region. I just wanted to talk about it broadly. I think we may bring this up in the roundtable. And this is the 90-day rule. For those who aren't aware, this is an Astro provision that if you have simple span girders made continuous for live load, you can use an assumption that a girder is at least 90 days old, and then you can essentially ignore continuity calculations. Continuity calculations can be challenging, and there's publication by PCA way back in the 60s that talked about this issue originally. There's an NCHRP that was done after that, and then the NCHRP results was then incorporated into the current Astro provisions. So it gets really complicated when you have odd span lengths when you're trying to do fixed end moments. But in general, this clause has created a little bit of heartache for producers, and I'll tell you why here a little bit later. So this is the general clause, okay? So the minimum age of the girder, and then we have to calculate the stress. And I'm going to break this item here into its components. So essentially what you want to do is you want to find out if 50% of the live load, the temperature gradient, the superimposed dead load, barrier, wearing surface, creep and shrinkage, and settlement. Settlement usually is not considered. You have allowable settlement in your design, so it's not going to impart a great load into the structure. You want to find out if those are compressive. Now, so typically your live load, because it's continuous member, and this is compressive at the bottom. So I don't want to go back to that, but this is all about positive moment connections. So your negative moment is in your deck, your positive moment is in the bottom of your girder, and you want to make sure that that location stays compressive. And if you do that, then you can make continuity earlier than 90 days. Other locations throughout the nation, they actually calculate two different continuity times. They calculate, say, like 28 days. After a 28-day break, they might do 60. And then in some cases, they'll even calculate 90 or 120 to see the effect the other way. In our region, we typically don't. We typically use a 90-day rule. We set it to basically the whole concept of unity, and we go about our design. I will tell you that typically these are compressive anyway, and then so we really have to worry about the creep and shrinkage part of it. So the pragmatic side of this is if all of these girders have to arrive to a job site and they all have to be 90 days old until the diaphragms are poured for continuity, it creates a very difficult relationship between the producer and the contractor and the schedule. So if a project is released in January, invariably the contractor wants to pour their deck, especially in the Northeast region, by summer. So if that job is released to the precaster, they have to produce the shop drawings. The shop drawings have to get approved. Then we have to go into production. We have to go into production of probably quite a few girders, typically at least a multi-span bridge in this case. And so they have to cure, make the strength, and all of them have to be ready by spring. Well, that's not pragmatic. So not always, right? Some projects allow enough lead time. Some girders are produced 2 years in advance. It varies by schedule, but a lot of times, because we're seeing a rapid rate to, especially in accelerated bridge construction, we're seeing that more and more of these products are having these issues. So how about a plan B? Why don't you just design a simple and detail for live load continuity? This provision no longer applies. Now, I don't think this is the best approach. I'd like to see the region, potentially do some analysis. I've done some analysis on the thermal gradient, for example, and how often that spacing and span length remains compressive. So that would be good information to share with designers. But a plan B is you just design a simple span. And typically what you'll find is that the end span of a continuous unit is controlling your design anyway, and you can probably work within the stress limits offered by Lrft or by your specifications and meet the service 3 stresses, and definitely on the interior spans. So that's been our experience. So I have a couple slides. I'm not going to go over them, but just to kind of show you, because I'm running out of time. But we've done some research on this in the past. The original NCHRP and that original clause was based on very low early release strengths, kind of a 4 KSI, 5 KSI design. This is actually an actual bridge in Virginia that we looked at, 62-foot span length, and negative is compressive. And so, yes, you need 90 days. And akin design you might use today might be a 45-inch bolt tee, PCEF shape, and you might use a 6.4 KSI release and an 8 KSI 28-day strength. Some of the questions that have come up before about strength. And you run the same math, and you find out you can make continuity at 40 days. So, this is newer materials. This is newer information. Unfortunately, the code is always a snapshot in time. It can't include everything. But I encourage this conversation in the roundtable and how that can affect producers. So this is my version of the fabrication issues that we run into. All right, so moving along into a snapshot in time and the code and how they try to keep up, let's talk about the future. So ultra high performance concrete. This is a subject I'm very passionate about. As stated, an opportunity to reinvent steel and reimagine concrete. So we can, again, I'm teamed up with Kortzoff at UHPC, and that's how we partnered with Precast Systems as well to do some cool stuff. All right, so I'm going to talk about what is ultra high performance concrete. I'm not going to go into too much detail to that. There's a lot of great resources already out there. In fact, recently at our ACI 239 meeting on UHPC, everybody did a presentation and didn't even talk about what is UHPC. So it's pretty cool. I think a lot of people are understanding what the material, the technology is, and what's out there, and what it can be used for, or you have experience firsthand on existing projects. So I'm going to talk about where UHPC is currently being utilized in the U.S., and who else is using UHPC, and then where could we use UHPC as precasters, producers, designers. So there's a great resource, the PCI UHPC webinar. So PCI has funded research on UHPC. Dr. Lawler and Dr. Tadros do an excellent job, about an hour long. They're going to talk in much more detail than I will about the material science of this, the background, as well as the global background. We only have about a half hour to talk about this, so they give great detailed information, and so I highly recommend going on the PCI website, continuing education webinars, and then finding the February 18th webinar. Most of my experiences with the Federal Highways UHPC designation and the research, so I'm going to be talking about more of that. Reid and myself, we actually serve on a technical review board for Federal Highways work towards a guide specification, and so I'll be sharing some of those publications that are upcoming as well. Ultra high performance concrete has been debated about how to define it for a long time, and so we're just going to kind of set the tone that what I'm talking about today is a certain type of UHPC. Okay, there are non-proprietary UHPCs that are coming on the field. There are proprietary UHPCs, which are pre-bagged and pre-mixed. But in the end of the day, whether it's not, even if it's non-proprietary and it's done at a producer's site or in the field, it's still proprietary to an extent because you have the know-how to make it work. Just like our high performance concrete mixed designs are now. So ultra high performance concrete is really just an extension of high performance concrete with the addition of steel fiber. So we're using low water cement ratios, less than 0.2, water to binder ratios of like 0.15, and we're using high volume fraction of steel fiber, 2% by volume. We use a lot of admixtures to make this all happen, and I'll kind of show a little slide about that. So we have a post-crack tensile strength of around 1 KSI, and most of the material characteristics I'm going to be showing you today are 1.2 KSI, and I'll go into that in more detail, but there's lots and lots of publications that are available currently for you to review more about this information. Federal Highway currently, because they're working towards a guide specification to deliver to Astro in June of this year, this has been an ongoing project and will be a really big step for UHPC to be used in structural elements. So this is a variety of publications they're working on, a standard method of testing for uniaxial responsive UHPC, which is an Astro comp provision, which would actually allow it to have a standard for using the test, which has been an impediment. Various journal behaviors, mechanical behavior, interface shear, flexure, shear design, pre-stress loss, all of that is coming through various publications. You see ACI materials, ACI structures, and they're all being approved through the Federal Highway Office of Public Affairs. So I asked if I could share this, and I was told I could. So there you go. So what is UHPC? As I said, it's steel fibers, high volume fraction, chemical admixtures, a lot more cement, sometimes up to double. You don't typically use fly ash and slag cement, although some do. You typically have a high volume of silica fume, say 10%. You don't typically use coarse aggregate. A lot of UHPCs do not. There are very few that do. And so your largest particle size is the sand. And then, of course, you use water. You use about the same water you use now. The admix you use about an order of magnitude more than your high-performance concrete mix. So what you get is a highly compressive material, 22 KSI, let's say, for argument's sake. Minimum threshold for UHPC is, as stated by PCI, ACI, CSA, and a few others, is 17 KSI. And some people put it in two classes. We can get breaks up to 30 KSI. So compression is pretty amazing stuff with that volume of cement. But what's really great about the material is the tension. So you're getting an elastic plastic material or strain hardening material after first crack. So first crack here is a pretty low strain. but you're able to have very, very, very small cracks, retain stiffness up until what they call localization. So localization is typically around 4,000 microstrain by design, but you can see it continues beyond that. So these tiny little cracks form, then boom, you get a localization crack. And that's the behavior we see in large scale and small scale specimens. You can see it here. This is the Uniaxial Test. It's been modified slightly since this in the Astro publication, but you can see where that localization crack occurs, which is a large crack. And after that, deformation ensues. So what does that look like in a larger specimen? These are two products that Precast Systems Engineering was in charge of producing. We actually got a contract for Federal Highway. So the top was produced in New Jersey with one UHPC. The bottom was produced in Florida with Durastress out of another UHPC. And they have the same design, which is depicted on the right. These are 0.7 strand. They have a 3-inch web. They have no shear reinforcement whatsoever. And although the first crack differed between the two materials, so this one actually has a higher first crack, this one has a lower first crack, the localization strain, the total moment at localization, or total shear at localization, was within approximately 3 kips. So what happened was, first crack was higher over here, so the load to first crack, but the load to localization was equivalent to the load to localization here. The first crack was lower here, but the strain was longer, if that makes sense. So probably does to the structural engineers. What was, I think, remarkable about this is that these two girders were cast in different ways with different UHPCs, and the result of the shear model was a nearly identical failure load. So that's really kind of shows that UHPC is truly market ready. Again, the PCI webinar does a great job of explaining all the durability characteristics of UHPC. Chloride ion diffusion is what some people measure. Coulomb values is what some people measure. Treat island specimens have been there for a couple decades. And the ASTM C1856 is a resource that you can use today. It's an approved ASTM that we use for UHPC. And you can see the order of magnitude better in chloride ion. If you want a Coulomb value, you're usually looking at, for a steam cured specimen, less than 100 coulombs. For a ambient cure, less than 300, maybe, for typical UHPC. So pretty incredible stuff, and I encourage you to learn more about it. All right, so let's move into the nitty gritty. So where do we know about UHPC being used? We know accelerated bridge construction typically, right? So using it for joints is just an obvious material. What used to be the weakest link is now one of the strongest. And the precast material cracks and the joint doesn't. So we don't have leaky joints. We don't have post-tensioning. And there's a guide spec that's out there. And this particular application has been studied since the early 2000s, really. It's a great deployment of UHPC. It's really exposed the opportunities domestically, and why a lot of us are pretty excited about it. Where else is it being used? Well, link slabs or repair of link slabs is an often place, or new link slabs. Bridge deck overlays is a whole topic that a lot of folks are very interested in rehabilitating bridge decks, repair of bridge piers, and then repair of corroded steel girder ends. There's some testing that was done at the University of Connecticut and implementation in Rhode Island. That's really good. Globally, well, really, other folks are ahead of us. So the French were really pioneers for UHPC, and so they have a 3-part code that's already established that's being used globally. The Swiss also have a published standard, which is not quite as in-depth as the French, but a very good first principles approach. They were very much on the leading edge of UHPC. And recently in 2019, the CSA adopted in Annex U a UHPC specification, which is for really all fiber reinforced. They want it to be for all fiber reinforced concretes. So one of the things that got me interested in UHPC was going to Malaysia. I had the immense pleasure to go with the PCI Technical Quest in 2016 and meet this gentleman with a water bottle, Dr. Vu, who many of you may have heard about by now. Just an incredibly energetic individual who's both a research scientist and a designer, and has accomplished over 175 bridges out of UHPC. Record spans, record practices, and really we're still well behind what he's accomplished. So I published an article about this in 2017, I think it was, which depicts that whole trip. There's also a publication in Aspire on the same event. So here's kind of what he's doing now. If you read those other publications, you'll see other projects. But I thought this was really cool how he just keeps growing his product model. So this 180-foot span, about 13'2" on center, 55-inch deep tub. It includes the deck. The deck was actually post-cast and installed with UHPC. And then one of his fundamental philosophies of his plant is that basically one product is one batch. I think that's why the deck was cast secondarily. So this is actually a span up top here. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9 segments. So around 20 feet apiece. And he's able to stack them. Very much a refined finish that you can get out of UHPC, and I think Dr. Vu's work is very elegant in that regards. This is actually a diamond plate finish. We were standing on that bridge in that picture before, and that was cast upside down. So that's actually UHPC on that finish. All right, so what are we going to do here in the United States? We've talked about this quite a bit. So I'm the chair of the subcommittee to the Committee on Bridge and PCI, and we've looked at various options of how to implement UHPC swiftly in the United States for structural elements. And how do we do that in advance of a code or along or concurrent with a code? So the PCI research is really focused on beams primarily. And so we looked at other elements. My background's more in the marine sector. So this is kind of a marine bridge, if you will, but certainly can be applied to land-based structures as well. So the committee voted, and we decided that piling was actually our best fit. But that doesn't preclude the use of UHPC and other elements. We just are focusing on piling right now, as most precast pre-stressed piles are driven. Therefore, you get immediate results on their performance. But I will say that in other cases, UHPC just makes a lot of sense, because if you have a place where you have a lot of labor, you have a lot of material, and typically the rule of thumb is if your pounds per cubic yard cost is like $1,500 to $2,000 cubic yard, well, let's look at UHPC. UHPC, you can usually get about half the section. In this particular case on the left, crack control actually governs. So wouldn't you like 2% by volume discontinuous fiber to help control those cracks, or help you operate with tensile strength? Or exotic materials, this is stainless steel rebar and a segment with epoxy. Gets to be pretty complicated. So if you can actually omit all that steel or most of that steel, you can really streamline your casting. So, sorry, I didn't realize volume was on. Volume off. Okay, very good. So you can see on the left, this is a girder setup for UHPC. This was actually the test specimens we made down in Florida for Federal Highway to test. And on the right is actually an H-pile casting, but I just wanted to give you an idea of the flowability of UHPC. A lot of folks may or may not have seen UHPC before, so you can just see how well it advances. It's self-leveling. It's thixotropic. As long as there's an advanced head on it, it continues to pour. This pile was 140 feet long. It was not spliced. It was cast in multiple lifts and driven effectively. So piling is really kind of our current task within PCI, or at least regionally as well. We're really excited about piling. The H-pile, there was a study done in 2008, which I'm going to show on the next slide. But essentially, you can get the same weight as you can out of steel. And if we're comparing to steel, so if UHPC is compared to steel, not concrete, it's very cost competitive. And you get the advantages of the weight, like you want out of steel, and durability that you get out of UHPC. So we're like I said, we're pretty excited about this. You can see the effective pre-stress here on a section such as this. The section might be only like 60 square inches. You're getting a 3.5 KSI effective pre-stress. For those who design piles, precast pre-stress piles, you're usually around 1 to 1.5 KSI maximum, maybe in extreme cases 2 KSI. So we're getting a 3.5 KSI on a material that has a high compressive strength, which you typically don't need the compressive strength for piles because the soil interaction governs. So that's the other advantage, which I'll show you in the next slide, that you get more bearing out of this. Even though it's relatively a low displacement pile, you do get some bearing out of it, which increases the overall capacity. And we think it will also shorten the pile. So not only is it competitive at first cost on a pound, cost per pound basis, but it can be shorter, therefore making it very viable. We're going to do some pilots here in the next couple weeks on pipe pile. We think pipe pile is an extraordinary opportunity. A lot of pipe piles in the Northeast market, and we want to make them out of UHPC. So if we take, I'll go through kind of some rule of thumbs here in a few other slides. So, we're standing on the shoulders of giants. So back in 2008, a whole research was done on UHPC H piles. This was a 10 by 57 replacement, and it weighed It was 10 inches by 10 inches and weighed 57 pounds per foot. They noticed that it had the similar lateral load behavior as the 10 by 57 on the weak axis. It had no shear reinforcement. There was no damage to the pile during driving. I'll show you another slide of that. And there was an 86% increase in the vertical load that was available in the comparison of the two piles. So this is a very compelling argument to use this type of material. So folks have latched onto that. Cortoff has done a number of demonstrations. They've done a square pile where they drove it as hard as they could with the biggest hammer they could find to find no effect at the top. They drove it faster. So that's one thing that when we talk about the design of piles, we don't necessarily talk about schedule. But if you're thinking that you're going to drive these things faster, especially in a marine environment where the equipment can be very expensive, that is a very, very positive add. This was actually a 30-inch deep by 30-inch wide H pile with 5-inch web and 5-inch walls. So not necessarily as small as what I showed previously, but again, they cast that was the 140-foot long piece. They were able to drive it again as fast as they wanted to, and the pile was actually had a lot of stick up. So that's part of the research needs is to figure out exactly that soil interaction and how long the piles need to be. Because if you have 40 feet of stick up, then that from economy of scale, it doesn't make a lot of sense. Other components. That's enough about piles for now. Slabs, deck slabs. So there's been a waffle slab pilot projects that have been done in Iowa. Again, Iowa has kind of been a leader in this industry in the domestic United States with Dr. Scherthred and Dr. Ailetti. So the waffle slab here is from Wapello County. It was tested in punching shear. The punching shear was, I think, 160 kips or something like that on a 2x2 prism. So incredible punching shear resistance in a 2.5-inch thick shell. There were ribs that were transverse to traffic and longitudinal to traffic. And so you can see that kind of depicted here. And it was mildly reinforced. Well, I'm a former fabricator. I don't necessarily care for the longitudinal ribs to the direction of traffic. So we've been actually working on a different system that would have only transverse ribs. And to be fair to Iowa State, they also studied this. But we've done a more advanced study. This is a non-finite element, a nonlinear finite element analysis, which we're going to be following up with testing soon. This is a 10-foot spacing on the girders, and we alter where the HL93 loading is. We also checked fatigue and ultimate, and we found that indeed you do not need the longitudinal ribs. The live load distribution was adequate. The deflection was adequate, and actually the stiffness of the system was better, as you'd expect, because it doesn't crack. One little interesting thing of note, we always think in stress, in pre-stressed concrete, pre-stressed design. UHPC is a little bit different because we have that post-crack tensile strength or sometimes hardening strength. So we're looking very closely at operating strain levels, right? So if 4,000 microstrain is your localization crack, which would be a big deformation driver, what's a good operating strain limit? Not stress limit, but strain limit. And so that's something we're working on and we're studying, and I think it's going to be an interesting. That's for mildly reinforced. If you're pre-stressed, your elastic system anyway, you're usually below your first crack, and that works well. So what about other components? Box beams is something we've looked at for a while. So this is a job from, actually this is a high ADT route that had a UHPC joint. This is in Staten Island, produced by Precast Systems Incorporated. And so what would that look like as a UHPC alternative? Astro says you have to have a 7-inch deck. We're working with Chapter 5, of course, but Chapter 9 might govern that depth for a while. So just make it 7 inches, fine. And actually, what you'll see a lot of times with UHPC is corrugation makes the most sense. It's the most cost effective. It's the judicious use of the material. Gives you the same stiffness. I guess one thing that should be mentioned, this is a 4-foot by 4-foot box beam. It spans 98 feet. This is a 4-foot by 4-foot box beam. It spans 98 feet. This one weighs 50%. So you're saying, well, why don't you make it shallower? Good question. But in general, the EI, the modulus elasticity of UHPC is not that much higher than concrete, and certainly not equivalent to steel. So, you're looking at, say, 5,000–6,000 if this is a 10 KSI mix, and this is probably 7, maybe 7,500, maybe in some cases, in unique UHPCs could be 8. But nothing to really, to go over the moon on. But because you have less cross section, you can put more pre-stress. You have more pre-stress, you can allow yourself to make up that delta in the deflection. So some of these designs are actually deflection controlled. Again, the PCI webinar gets into this in more detail. Some questions that you may have is what about long-term effects, losses, things of that nature. For pre-tension elements, you're looking at pretty similar losses to what you have now. There is early age autogenous shrinkage that occurs, which can be on the order of 500 to 600 microstrain, but your overall shrinkage might only be 900, so your service shrinkage is actually very low. So the precaster has to accommodate that early age shrinkage, but once you're in service, you're very stable, especially if you go through a post-cure. Secondary cured elements exhibit better stability, better volumetric stability. The creep, especially for post-cured elements or seam-cured elements, creep is also very, very low in service. So your early age creep may be a little bit soft, but your long-term is much higher. So, much lower, resulting in, so for an adjacent member, there's kind of an ideal material for it. Dr. Vu in Malaysia, you saw where a lot of those elements are post-tensioned, so your losses might be in the order of 10%. So post-tensioning makes a lot of sense for this material as well. Anyway, I could go on, so I'll just move forward. If you have any questions, please bring them up. If we can't answer them in the roundtable or in the Q&A session, I'll be happy to answer them otherwise. I guess one other thing that's novel is the DAP. We've looked at this a while back. We haven't built one yet. We're very interested in building one. And the 20 inches is completely arbitrary. This could probably, by design, be something like 8 or maybe 12 and have enough shear capacity. In many ways, UHPC is kind of a strut and tie designer's dream because, you know, oftentimes you're trying to put so much reinforcement to prevent cracks, and now your mix has all the crack prevention you could ask for. So adapt ends make a lot of sense. And so some folks, you know, when you have a grade crossing, you have a grade buildup in order to do a bridge crossing, DAPs may be a thing of the future. Ironically, they're a thing in the past. I think as with all products with UHPC, things we did yesterday may be valuable again with UHPC. Some of the flaws that were inherent to details of the past may be overcome by tomorrow's materials. And lastly, I just want to say from a form standpoint, you know, this 4x4 form is exactly the same. The only difference is that the void's bigger. So from a fabrication standpoint, it's super easy to implement. And even these ribs can be glued on or cut. You can do a variety of things with polystyrene. So if it weighs 50%, this is a little teaser. If it weighs 50% at 4 feet, why not just make it 8 feet and have less joints? Sure, why not? You can do that. I showed you a span of the deck it was actually an 8-inch system that went 10 feet. So a 7-inch system that goes with double ribs at 8 feet is certainly viable. Hybrid elements, I won't go into too much detail of this. I just want to show that there's other options that's out there and some testing that's been done. Standard with FDOT has actually tested this joint. We wrote a paper about it, which I'll show you in the next slide. But what if you just take your end zone of your long span girders, you move your lifter's way in for lateral stability, you don't have to worry about topside tension. You go from drape strands, 20 drape strands, you go down to all straight strands, make it a little bit easier to fabricate. You pour the middle with lightweight, so you bring down the weight of the girders. You allow greater spacing, so you go from 9 girders down to 7. You know, this job had 200 girders. You do away with any end zone cracks. These cracks were actually pretty big, so they had to be injected. All of that value by just supplying UHPC at the very ends. So we wrote about it. We investigated it, and obviously 205 is an arbitrary number. It could be 300. It could be 400 if you can ship it by a barge. That doesn't matter. What matters is that we looked at the joints between the UHPC and lightweight or normal weight concrete, and as have a lot of other folks on Interface here. Similar in concept, segmental construction. We've worked with the ASME segmental design manual led by Nick Amico from HDR. Parsons was on that, and a few other folks. Great group of people to work with. So you can make the segments, a couple of the segments out of UHPC, make the rest out of normal concrete, or you could do something perhaps in the future where you're making some sort of frame like as shown. So conventional versus this truss system. So we do a lot of marine work. There's a lot of precast caps that are coming in the region as well. There's some fantastic research that's being done in FDOT on large bar diameter. This is preliminary, just FYI, but large bar diameter closures. So you can see here that with 2 3/4 cover, you can develop a bar in 11 inches in UHPC. So typically your cover is going to be governed by your precast anyway, so you're going to have 3 inches of cover. So that's I think that's pretty amazing. If you can go down to 1 foot closures on number 11 bars, then precast concrete caps certainly have a lot of viability. And it's kind of just a general slide. We do a lot of shells, so actually check the shell. This is a 3-inch web. The 3-inch web has the same shear capacity as this entire composite element. So if it's non-composite or composite, it really doesn't matter. You can do waterline footings like this. We've done large waterline footings. You can shell them out. You can corrugate the webs. So, and then one of the main things is shipping. A lot of folks don't realize when you talk about cost or first cost or second cost, shipping becomes a major issue. So back to that hybrid element I showed you, reducing the number of girders, reducing the weight, decrease the piling length. When you run through all those numbers, the cost to the contractor is competitive at that bid. So you have to really run through all of it. The cost of the material may be expensive, but the labor savings, and then they get their crane savings. And really one of the benefits of all of these things I'm showing you is that the means and the methods of the contractor is essentially unchanged. So we're, you're doing novel things with material, but once they get to the crane's hook, they look pretty much like concrete or steel. So at any rate, I always like to show this slide. I think it's very indicative of UHPC over the years. It's a really innovative approach, but I'm afraid we can't consider it because it's never been done before. And this is starting to change. So keep an eye out for UHPC in the future. And I'm sure more and more of the producers will be issuing, ideas that you can use in your region, either as design or as an owner. Thank you. Turn it over to Mike.
Thank you. Let me fire up my. Let me know if you can see the screen. I got the share. You can. Great.
Yes, sir.
Okay, it's my pleasure to be here today to talk about Next Beams. Next Beam is a innovative section that was developed by the PCI Northeast Bridge Tech Committee many years ago, back in before 2009. We're here to talk today about a recent update that was issued in January, which is the January 22nd to be exact, which is the second edition of the Next Beam guidelines. The key thing about this that I'd like to reinforce today is that these are guidelines, guide details. They are not standards. A lot of people think they're standards, but they look very much like standards. But we still need people to actually design the beams and design the reinforcing. But we give an awful lot of guidance on how you can actually design and detail a Next Beam bridge.
And Mike, I'm not sure we're seeing your screen. I'm not seeing your screen.
I thought that might have been the case. Hold on 1 second. Hold on. I just got to share. Thank you, Reid. I appreciate that.
Sure.
There we go. Let me start it up again. Should be able to see it now.
Looks like you're sharing it. We see files.
I'm getting there. I'm getting there. And here we go. There we go. That should be better.
Looks good.
Thank you. So again, as I mentioned, the Next Beam was developed by the PCI Northeast Bridge Tech Committee, which is where the NE comes from in the Next Beam. It was originally intended to be a Northeast section. The popularity of this section has gone beyond our wildest dreams as far as how many states might use the section. So that's why it's important today that we're presenting it for the entire East Coast. And we're seeing it starting to move west as well. As far as availability of documents that we're going to talk about today, the guide details are available at the PCI Northeast website. It's www.pcine.org. You can download both the guide details that I'll be showing quite a few of today, and also we published a document, a history of significant changes made to the guide details, going back as far as 2009 up to the current guide details that are available now. The basis of this presentation today are the major changes that occurred in the recent publication of the second edition in January. I mentioned before, this originally was intended to be a Northeast section, and this is a map of the U.S. And if you look on the map, there are 19 producers now in the US that have forms to build next beams. We get that question asked quite often, who has forms, and you'll see that we're going as far west as Texas. I know states such as Utah and I think even New Mexico are considering the next beam. So it is fast becoming not just a regional section, but becoming a national section. But if you see here, it's definitely a Northeast Middle Atlantic section, because there are quite a few fabricators in our region that can produce this product. So as we move forward, we're seeing more and more states accept this as a standard, and the use has been quite exciting to see how many people are actually getting involved in this. So it's been a tremendous success of our committee. Rita mentioned before the committee members, which includes state DOTs, consultants, and fabricators. So it really was developed as a collaboration between all those entities. And from day one, we always intended this section to be a fabricator-friendly section, meaning it's easy to build, easy to fabricate. We do not require forms to be broken down and assembled. It can be poured, lifted out of the form, and a new piece can be built quickly right after, which reduces the cost of the product. So that's something that we wanted to do, come up with a cost-effective section for short to medium span bridges. A little bit of history of the details. As I mentioned before, the first set of details were published in 2009. At that time, we had two different beam types, an XF and an XD. I'll explain that in a minute, what those are. And there were separate details for each. In 2015, we combined these into one set of details, and we switched it to an 11x17 format. Before that, the previous version was an 8.5x11 format, and we just did not have enough room to put all the details and notes on these smaller pages. So we went to 11x17 format, which worked out quite well. There were some changes that were made in October 2015. We changed barriers. We originally showed the next beam with a lighter weight open rail metal barrier to see if we could push span lengths a little further. But the reality was most of our owners were using concrete barriers, which limited span lengths. So we switched over to concrete barriers in 2015. 2016, we made some modifications to some of the details. We moved the location of top strand to facilitate fabrication. 2017, we added some span length tables, very general span length tables. They're not exact because they are based on about 15 different assumptions. We actually list the assumptions. So too often we're having designers go to those tables and take those numbers as being exact. They're approximate, but they'll get you in the ballpark, especially for something like a type study. January 2021, as I mentioned before, a major rework was done. The entire document was reworked from cover to cover. We updated a lot of details, really cleaning up details and making them better. And that's the focus of this presentation. So let's dive in. For those of you who are not totally familiar with next beams, we have three different versions of the next beam that are included in the guide details. The first one that was developed was the next F, which is shown on the top of the screen. That is a 4-inch lightly reinforced top flange. The intent was F stood for form. That the idea would be is the beam would be not only the structural beam, but also be a stay-in-place form to support a fully reinforced top concrete deck, cast-in-place concrete deck, typically minimum 8 inches thick. Soon after, we developed the next D beam, which is shown on the lower right. And the intent here, this is a decked beam where the top flange actually is the structural slab for the bridge. It's a fully reinforced top flange, and we have fully reinforced connections between the flanges. So that was a real popular item for accelerated construction because you could build a bridge very quickly. The reality is also a next F beam is popular with accelerated construction because it still is rather quick to build a bridge with it, since we eliminate essentially 90% of the field forming. And the last addition we added in was the next E. The next E is a beam with a 4-inch top flange that's heavily reinforced, because the top flange is the bottom of the structural deck. And people ask the question, if F stands for form and D stands for deck, why did we come up with E? And the tongue-in-cheek answer is it's halfway between a D and F. The flange is part of the structural deck, but you still add a 4.5-inch topping that's reinforced to complete the structural deck. So these three sections are available. Certain states like certain sections more than others, and that's fine. We offer details for all three sections in the guide details, and we offer design guidance for all three in the guide details. So why did we update it in 2021? What drove this change? And there were a few things. We wanted to improve on the details. There's nothing wrong with the old details that were in the previous editions. It's just that there was always room for improvement, and we had better ideas from experience to come up with better details and to make these bridges even more cost-effective to build and easier to build. Another big change was in 2018, the Astro produced the Astro Lrft guide specification for ABC, which is shown on the right here. I had the pleasure of being the principal investigator for the research project that developed this guide spec, and we included deck level connections are a big portion of this document, including UHPC. So we felt there was a need to update the guide details to be consistent with the Astro Lrft guide specs for ABC, since this is an ABC product. So that was a driving factor. Another one was Rita gets numerous questions. I would say numerous, but she gets a certain number of questions from designers and owners about the use of next beams. And the questions really point to need for clarifications, things that we need to maybe put a little more detail on. Because if we see the same question asked 2 or 3 times, there's a chance that maybe our details are not totally clear. So we added a lot of notes and a lot of details to answer the FAQs that we typically get. And lastly, the Astro Lrft bridge design specifications had some recent changes to debonding that dramatically affect next beams. And the reason why is because next beams, as I said before, are considered to be a fabricator-friendly section. And one of the things that we did to make them friendly is we eliminated draping of strands. We have only straight strands with debonding. So obviously a change to the Astro provisions for debonding had an impact on the span lengths and the design of next beams. So let's go through the changes that occurred in 2021. I'll pick them off one at a time. And the first one is change number 1. We added additional information that we had previously on the website. We added introductory information, things like the committee members that have worked on the document. They're listed here on the first sheet. We added some nice pictures of some completed projects and some graphics. We also added introductory statements on how whereabouts the development came from. Change 2, the frequently asked questions. Previously, we had these listed on the website where you can download a FAQ document and go through that to answer questions that you might have. We felt as a committee it was important to get these FAQs into the actual document. So we added them on the introductory pages in a 2-column 11x17 format. We went through the FAQs, we updated some of the answers, we added more FAQs, and you can see the subjects that we cover. We organized them by subject. We have 8 questions on general concepts. Bridge geometry are 9 FAQs, design 14, deck and mooring surfaces 3, and railings we have 3 FAQs that we've covered. So if you're going to be designing one of your first next beam bridges, I really encourage you to read these FAQs. The answer 95% of the questions that
sorry, yes. One sec, I've got
we have somebody on microphone here. Okay, change number 3. We felt there was a need to show the design section of the beam. Essentially, what's the form look like? We have questions all the time posed to us. Things like, well, how wide can I make the beam? How deep can I make the stems? So questions like that. So we decided to add a simple detail showing the design envelope. Essentially, this is the sandbox that the designer can play in to produce a next beam. So this is the form. This is what the form looks like. And if you could fit the concrete section that you desire in that form, it can be built. What we recommend you do is if you have something that's non-standard and non-typical next beam, you contact fabricators or PCI to see what are the limitations. Like often we've been asked, can we make a beam shallower than the minimum depth shown on the standards? And in most cases, you can do that. I just said the word standards. Now, guide details, it can be done. A few things are fixed. The width of the stems and the spacing of the stems. That is a hard dimension because that's a steel form and that is where it's locked in. Items such as the thickness of the top flange can vary quite a bit, so that's not an issue. And the overall width of the beam is limited to 12 feet. So these are the major things that cannot change, but everything within that box can be modified. I mentioned before, debonding limits have changed in Astro, and I won't go through those Astro provisions. It's about 2 or 3 pages of specifications, but we went and took a look at our next beams and came up with recommended potential debonded strand locations for next beams that are consistent with the Lrft bridge design specifications. Key things to keep in mind, there is some interpretation as to what the Astro Lrft design specs call for with regard to double T's. So with regard to outside strand and interior strands and things like that. So our committee basically went through the Astro provisions and came up with our interpretation of what the Astro Lrft is calling for debonding. As I mentioned before, the ABC guide specification is out, and we wanted to include that. So we have developed revised details for deck level connections, specifically for next D and next E beams that are now consistent with the Astro guide specifications for ABC. We also changed it such that you can use different fill materials. Previously, we had limited it to at one time 6,500 PSI grout. Now you can design this joint with normal concrete if you desire. You can use UHPC if you desire, and you can use high strength concrete or high strength grout as well. And we give equations for where now a designer can not only change the material, but actually could design a joint to custom match the fill material that you want to use. And we've included tolerances in these details. So now it's very easy to detail that connection for your particular design. One thing we do recommend is using exposed aggregate surfaces for the edges of the next beam flanges. And that's really less of a strength thing and more of a durability thing. Early UHPC joint work done in New York State and federal highways showed that there was some issues with minor leakage to UHPC joints at the interface between UHPC and the precast concrete. The exposed aggregate takes care of that issue, and you get a much more durable joint. But the key thing is we like to reinforce, and the ABC guide spec reinforces this as well, is we do not need to specify an actual amplitude. And people are specifying 1/4 inch amplitude, which is fine. It's just difficult to get a 1/4 inch amplitude on precast concrete. The 1/4 inch amplitude comes from the Astro Lrft design specifications for interface shear for composite action between girders and concrete decks. This is not, and that's a structural interface shear calculation. The interface between the precast and the UHPC, really, it's a reinforced joint with a geometric shear key that provides the shear transfer. We're really not looking for bond per se of the fill material against the precast. So really, we just need to expose the aggregate, not have a specific amplitude. If you feel a desire to specify an amplitude, we recommend an 1/8 inch amplitude. Really, 1/4 inch amplitude should not be necessary and is excessive. And we're hearing stories of contractors spending an awful lot of time trying to get to that 1/4 inch amplitude when it really is not necessary. And this was verified with federal highway as well as acceptable to just expose the aggregate and move on to have a good durable joint. So we've also developed details similarly for the next E-beams, similar equations and similar details where we are accounting for not only the width of the joint, the lap length, but also the tolerances and how to actually specify these joints so that they fit together in the field. Change number 6, we modified some of the skew requirements for these beams. Previously, we had limitations that we've updated. We've also simplified some of the details. We'll go through that in the next couple slides. We found issues with confinement bar details that people were not necessarily following the Astro Lrft bridge design specifications exactly. So we've added in the lower right corner a detail of a side view of a stem showing the reinforcing layout and what you need to design for as far as splitting zones and confinement steel and stirrup spacing for confinement. So we try to clarify common issues we've seen with beams going through the precast plants. We've eliminated splayed bars in the top flanges. I'll go through that in a minute. And we've changed the skew recommendation for next beams. Next Ds used to be limited to 20 degrees. We've increased it to 30 degrees. A lot of it was based on some of the details that we've now developed. Also, the limitation previously was set with issues with cracking on next F beams, which I'll go over in a few minutes. But really, those issues have not really manifested themselves in the fabrication plants with cracking of D beams. So we've increased the skew to 30 degrees. Now, we often are asked questions, can we do a next D at 40 degrees, or 32 degrees, or 31 degrees? And the answer is probably. We're fairly conservative with these skew angles. If you need to exceed one of these skew angles, my suggestion is you contact PCI or a local fabricator and find out if they have experience with higher skews. I do know of certain next D beams being fabricated as high as, I believe, 45 degrees. So it can be done. This is just showing some of the simplified details. Previously, the next D and E beams had splayed bars in the top flange. And at some point, we all realized that all of our details show an end diaphragm that is supporting the edge of the deck at the end of the bridge. Therefore, there was no need to splay the bars, and we can now keep the bars square to the stems, and really greatly simplifies the details of these D and E beams. Another issue we found that there are provisions in Astro for longitudinal bars. This is change number 7. If your stresses exceed a certain limit in Astro, they do recommend that we add longitudinal steel, and these provisions have been in Astro for a long time. We were finding that some next beams designs were coming out where designers were not following these details strictly. We never showed longitudinal bars in our details. We figured they would just add them, designers would add them. So we decided that no, maybe we should show them in our plan views, and you can see here we show additional bars, and we have a very detailed note on when you need to add these additional bars when your stresses get high. We made minor changes to diaphragms. This is change number 8. Previous versions of the next beam guide details had dapped top flanges to facilitate concrete placement. As a committee, we are now recommending that diaphragms be attached off the end of the beam. So we eliminated dapping the top flange. And the reason for this is we are seeing some cracking issues out of those dapped top flanges that were problematic. So again, we're trying to solve some of the problems that we typically see. So we modified the details to improve the performance of these products during construction. Integral abutments require more substantial end diaphragm. Previously, we had shown dapped top flanges. We decided to go with we scored off the end of the beam, eliminated the dap, and added portholes to pour the concrete to cast that end diaphragm. So again, we're trying to simplify details and eliminate problems with cracking in the field. Change number 10, on several projects we've had with next D beams, specifically with higher skews, the beam's not seating properly on the abutments. So if you're concerned about this, and it's brought on by a combination of skew and camber that causes this issue, the beam will teeter-totter on the 2 acute corners, that you may want to consider adding an adjustable bearing. The reality is you probably only need 1 adjustable bearing on each end. You could probably get away with 1 out of the 4 bearings, and that'll get it to seat properly, essentially going from a tripod to a 4-legged table with an adjustable bearing. These are expensive details, so we don't recommend them for every bearing, but keep in mind you can do adjustable bearings. We also have details for other bearing types that are with shims that can be placed to do minor adjustments. So we recommend you look at the details that we have and pick the right detail for your project. If minor adjustment is necessary, you might not need something as elaborate as this detail. If you think maybe we can deal with shims, that's probably a much more cost-effective way to construct these bridges. Change number 11, we had previously shown an actual utility, methods for hanging a utility on the next beams. Some of the utility companies did not like the details where we showed threaded inserts on the underside of the top flange. Some utilities like to have inserts in the stems. So we've now added details to show both options. We have notes basically saying to coordinate with the utility company for the way they want to hang their product. We show both options on our details now, and we've actually eliminated the actual utility we showed because we understand there are more than one utility on a lot of bridges. This is one of the reasons why next beams were so popular for short span bridges, is as compared to adjacent box beams, we did have the ability to handle utilities much more easily. So this is an important detail that we've cleaned up. Before we were talking about repair members, JP was talking about this before. We actually have repair guidelines that we've developed in the Northeast. We have it's similar to the national document, but as JP mentioned before, we've added substructures and deck panels as well. But we also have a repair procedure for the typical crack that we see with next F beams that are lightly reinforced top flanges. And you may not be able to see clearly, but there is a crack on the obtuse corner. This is a skewed next beam. On the inside of the stem, on the obtuse corner, we sometimes see a crack growing out of that corner. And this has to do with the way the beam cambers up in the form when you release the strand. And again, it's a lightly reinforced top flange. We have added a lot of reinforcing to control this crack, but we still see the crack occurring occasionally. The key thing is the reinforcing we place in the top flange is to control the width of the crack, not necessarily eliminate the crack. It'll keep the crack tight. But we have developed repair procedures if that crack is a concern, ways of sealing that crack to make sure that we have a durable product moving forward. So in summary, the second edition has many improvements over the previous details. If you have a bridge designed under the old details, you don't have to run out and redesign the bridge. The old details are good, but we've now come up with improved details. So that's an important thing. And again, I'll reiterate, the details we publish are recommended guide details, not standards. So there's no need to go back and rerun all your old projects. If you have time to do it, we encourage it. It is now consistent with the Astro Lrft guide specs for ABC. We've included deck level connection details, including tolerances and UHPC connections, which are very popular. We've included our FAQs in the file now, so you don't have to download multiple files. And now we are consistent with the new Astro Lrft design spec provisions for debonding. And again, these are all available at www.pcine.org. And with that, that concludes my presentation. I'll be sticking around for the panel discussion as well if you have more questions to ask. Thank you.
Well, good. Thank you, Mike, for wrapping us up there. And now it's time to go into the roundtable. JP and I will sort of get this going, and the others will participate as required. We have gotten some questions in from the group, from the chat box. We have a number of questions. So why don't we just kick out a couple of those? There was one, I think I actually answered it, possibly on debonding. Well, let me think about this. I think we're going to end up hitting these questions when we get into the questions as we go through and talk to, or let the pre-stressors work on things and respond here in the roundtable. So why don't we just throw it open to the producers right now. Change things just a little bit here. We've got three producers, Russell Dixon and Troy Jenkins and Mike Weigand, and we'll open it to them to see what they would like, or what are some common issues that they see. And what we'll do is we'll allow each of them one, and then we'll keep rotating through. So we'll start with Russell since his picture's on top, and then move to Troy, and then Mike, and then we can cycle back through. Just what's an issue that you feel like is something that you would like people to understand about how you make girders and how their decisions affect your production? Russell, you want to kick us off?
Yeah, thanks, Reid. One common item I see, and this is more from a total precast or ABC construction side of things, is a precast to precast joint detail. You know, just a little explanation on that. You know, we do have a joint considered a match cast joint. That is where you would have precast, you know, kind of almost a second cast, but you would have precast poured one day, and then you would pour up against that precast the next day. That is really the only style of joint that you can have where you have precast up against precast. And often that joint then receives a post-tensioning to apply some pressure across the joint just to get it back into position to where it needs to be. Often I see plans come through that have two pieces of precast adjacent to each other. And let me step back and just say match cast is, it's completely doable, but it's not real easy to do. It takes a lot more handling of pieces and different things like that. So, you know, what I see sometimes on drawings is two pieces of precast with no joint in between it. But match cast is really not practical. So in that situation, you know, it just needs to have some sort of a material in between the two, and typically that's a 3/4 inch or 1 inch grout joint that's between one piece of precast and the next piece of precast. So just something that I see often that designers may, or people not completely familiar with precast, it's a little different obviously than cast in place. Cast in place is kind of similar to the match cast scenario, but when it is precast, you got to have something to make up the difference. And some of the issues that you have, if you have precast on precast that's not match cast, you will get point loads, you will end up getting spalls, and you won't get the best product for what you need. So just kind of wanted to throw that out there.
Yeah, this is Mike Culmo. I like to throw in my 2 cents on that. We did a research project under NCHRP, Project 12-98, and part of that project involved looking at tolerances for precast. And we published a guideline document that solves that issue. Essentially, we come up with how to specify the width of joints between precast elements to get them to fit together properly without those point loads. So it's a document you can download for free. It's if you just do a Google search of NCHRP Project 12-98, and there's a guideline document. We're also going to post that guideline document on our PCI Northeast website. But it's a great document that not only tells you how to specify tolerances for precast bridge elements, but also tells you how to specify the width of joints, which is a common source of problems. So I encourage people to take a look at that document and go through that. It's a very easy document to work with, and a substantial amount of research went into that document to make sure that you have joints that work.
Okay. I guess my issue, I guess I'll say, and it kind of relates with Jason Lewis's question on RFI design issues or errors coming out of the contract plans. I don't know that I'd call them all errors, but if engineers, when they're designing a bridge, are coming up with something that might not be so standard, consulting the local fabricators or PCI Mid-Atlantic or Northeast is really a key, because we can look at some of those and maybe offer some solutions that are a little easier for us to build and eliminate the need for us to be sending the RFIs, with our localized expertise. Just because something's being done in Florida one way doesn't mean we can do it in Pennsylvania this way. Different constraints that we have that we might think about. So, that's pretty much our biggest issue that we're seeing. And it's mostly these specialty jobs, which could be precast, substructures or accelerated bridge, or just, something kind of new on the market. So that's the one I got.
Okay, well, this is Mike from JP Carrera. I'll pick up on Troy's point and say that similarly, we find that one of the biggest issues we have is having to generate RFIs early on when we first receive a set of drawings. And, we like to do the accelerated bridge projects, and obviously time's of the essence. But when you get in a set of drawings and we immediately feel like we have issues with detailing and some of the ancillary design that we need to do, that can delay things somewhat. Just as an example, I'd recommend that folks acquaint themselves with all those guidelines as far as the next beams go, New England bulb tees, whatever the product types they're designing, as far as where the strand positions are, so that we make sure that strands are in the positions where they're supposed to be designated. If we're detailing web reinforcement and we have hooks in the stirrups, or those hooks below the strands, and if there's a 90-degree bend in that bar, what is that radius, and does that really fit around the strand if the strands are detailed with, say, in the case of a New England bulb tee, 14 in the bottom row. So we may not meet clearances then for cover. So there are a lot of considerations like that we'll see early on and need to be addressed. That if that could be addressed beforehand, that would certainly help expedite the process. But I would say that's probably the biggest issue we see, that we would love to see improved.
Okay.
Russell, do you have anything else there?
I do. We can keep going. And this is just kind of for information. This is a difficult one. piece size. And this mostly, again, relates to total precast construction. But, you know, a general rule that we typically go with is try not to exceed your beam size or module size or deck member size. You know, something is going to be needed from a substantial crane standpoint to set that. So, you know, there's shipping constraints in a whole lot of different ways. And then from a production side of things, it's very, very difficult to narrow it down and figure out from a detailer's side of it, engineer side of it early on, to know exactly what size or how you should break pieces apart is difficult. So general rule is use the beam, you know, weight, and then overall size, try to break it up where it makes most sense. I mean, obviously if there's some skew or some angles, you know, kicked wing walls, you know, how your stresses are flowing in your footers, things like that can clearly, you don't want to put a joint right where your stresses are critical, you know. So there's some things there that you definitely got to pay attention to. But overall, the biggest thing that I can say on that is try to be flexible and try to be open to change if the precaster wants to present something a little bit different, you know. So because I wish there was a cut and dry, easy way, black and white, to say, hey, this is what you need to do, but there's not. You know what it's like from a bridge. There's every different scenario of angle and slope and skew. And so, you know, that really comes down to is being a little bit flexible, trying to keep them within range, not get too heavy, not get too large, but then be flexible at the end of the day. You know, if some RFIs come in to, you know, propose some changes, and generally I see that, and it's generally not a problem with that, but that just helps out. So just something else I wanted to note.
We had a good follow-up question here, asking, you know, how willing are the precasters to speak with the designers prior to release of the plans and specifications, and what is your experience in that in the past? Maybe I know, Mike, we had talked about that previously. Maybe you want to go first and then follow up with the producers.
Okay. Me, Mike?
Yes, Mike Culmo.
There's too many mics on the call. No, I think that you want to avoid RFIs. One way to avoid RFIs is to talk to a fabricator before you issue a set of plans. So if you have something that's a little bit out of the norm, I encourage designers to contact PCI or a local producer. As I mentioned before about next beams, we have guide details, but you can stray slightly from those guide details. Things have been done and can be done. So if you have a question, before you put something unusual on a set of plans, talking to the fabricators to make sure it's acceptable is always a good idea. Like the lateral stability that Reid talked about, we want to make sure something is buildable. So if you have something that a fabricator cannot produce, that just becomes a problem in construction and everything comes to a grinding halt. So please, if you have something that's out of the norm, you should definitely contact fabricators.
All right, Mike Wigan, you want to add to that?
Yeah, I mean, I'd say we're very open to talking with designers, and certainly we recognize it's very productive for all parties to have that initial consultation. So we welcome it whenever we can.
Absolutely concur.
You may want to, a good example of innovation, I think Mike Wigan can talk about that, but there was a recent project that MassDOT put out, I think it was Design Build, where they wanted to use next beam, but they couldn't make it work for I think it was the width issue, Mike?
Yes, I'm familiar with that job too.
They ended up changing it to adding some single T's that cut the next beam in half. So, this was asked early on of the fabricator, can I even think about this scheme? Do you, mix a next beam with a single T version of the next beam to get it to work? And with the fabricator input, that was how the job went out. So,
we had envisioned a single T, a half next beam for years. And it was a matter of time before it was going to come up. So we wasn't surprised when it did happen. And that's another reason why we show that typical cross section of the form on our sheets now, to say this is that sandbox you get to play in. If you can envision something, a good chance it can get built. So again, the key thing, the Northeast extreme T cross sections, all details I should say, were developed by a committee that included fabricators. So we have addressed most of the issues you're going to run into on a daily basis. However, there are also, if you're doing something, again, out of the norm, with any product, not just next beams, contacting a fabricator is a great idea.
And just to understand too, we're always open to anyone stopping in for a plant visit.
Yeah, definitely. We answer a lot of questions. We get a lot of phone calls from the Pennsylvania design community. A lot of common questions of concrete strengths, draping, the bonding, and I mean, I can answer some of those right now, but like,
why don't Troy, that's a good segue. Troy, why don't you talk about draping versus debonding and typical design preferences?
So our preference, and this is one of those things that every plant is a little bit different. One, we removed our debonding system for box beams. After 60 years of the steel contraptions being under live steam, we felt that it probably wasn't safe anymore for all the corrosion that happened to the steel system that was in our beds. So we don't make deflected box beams anymore at all. Bulb tees, unless the design requires it because of, you're pushing the beam section, we typically prefer straight strand debonded for beam lengths up to about 130 feet. Over 130 feet, we don't mind it being straight, but deflected typically is a little more cost effective for us at that longer length. Concrete strengths all depend. I mean, every state has a couple rules. Our biggest thing is if you can keep the release strength as low as possible and still meet the stress limits, we can turn the bed over a lot faster. Guaranteed. Just got a phone call yesterday from an engineer that he asked if we can use a 9,500 PSI release strength, but he only needs 10,000 for 28 day. We can do it, but we're probably going to need about a 12,000 PSI mix to make that work. So
I think just like to add, Troy, from a designer's point of view, is that we get asked the question a lot, like what is the percentage of the final strength for the release strength? Is it a 0.8 or 0.6 or 0.7? And the answer is there is no Astro provision for percentage of design strength. Right. The release strength is what you need for release, what to keep your stresses from cracking. So we always try to tell people is the release strength should be whatever your calculations say it should be, and don't round it up or raise it up. I've seen people say, I need a release strength of 3,600, but I'm going to specify 5,000, thinking they're getting a better product. Right. All you're getting is a more expensive product. It's going to sit in the form longer. It's a temporary condition. The final strength is the most important thing for durability and strength.
The only caveat I have to that, Mike, is you have to know your design program, because some design programs calculate all of the cambers based on the release strength and don't take into account 28 day.
Yeah.
And your cambers that you're putting on your contract plans are not going to be indicative of what the beam is. As a fabricator, from my standpoint, we always protect ourselves by calculating the camber ourselves and sending an RFI to say, this is what we believe we're going to have. But
which leads into a great mention of our PCI Northeast has issued a document on camber and profile management mostly for decked beams, but a lot of the stuff in that document is good for any beam. And we do recommend that approach, that the designer does their best to calculate camber based on a whole bunch of assumptions, including the final strength of the concrete. As Troy said, you might specify a 10,000 PSI mix, and he may give you a 12,000 PSI mix to get the release strength in the time he needs it. What is that? That has a major effect on camber because it's a whole different concrete than what the engineer assumed. So we do recommend that engineers do their best to calculate camber, but allow the fabricator to recalculate camber and then come to an agreement with the designer of what the actual camber is going to be. Adjustments to drawings may be necessary. Things like beam seats may need to be adjusted. And the key thing is also that new camber should be the camber used for measuring tolerances in camber. Go by that revised, essentially set a new bench for what the tolerances are measured against. Mm-hmm. So it's a great document you can download from PCI Northeast.
Okay, I'd like to pass the drape and debonding conversation to Russell. Russell, do you have a few comments on that as well?
Yeah, I have to agree with Troy. You know, if you had an option between debonding and drape, definitely, and specifically on box beams, we also do not drape box beams. So if we're going to control stresses in box beams, it has to be with a debonding situation. But from a draping situation, you know, you tend to get, you know, you hate to say it, but higher stresses to follow the strands sometimes create some cracks in the sides of the web of, you know, bulb tees or I-beams from drape strands. So let alone the extra work, increased costs to you know, do the draped harp strands, extra hardware, different things like that are more costly. So from our standpoint, absolutely, we would prefer to do a debonded beam over a draped beam, you know, all the time.
And round it down, go ahead, Mike Wigan.
Yeah, just similar to Russell and Troy's comments, we would much prefer debonding strands versus drape strands. You know, it's just definitely our preference. We do still some box beams with drape strands if it's specified in that manner. You know, one of the things too that the designer needs to think about with the drape strands is interference of post-tensioning pockets or inserts, utility inserts that might be specified in a beam. We tend to see there a lot more potential for conflicts when you're draping strands as well. So that's all a consideration that needs to be taken into consideration as well.
And
Yeah, and I guess Troy's rule of thumb of 130 feet or greater, I say, could sometimes be omitted by top strand debonded, right? Mm-hmm. So if you have those strands at the end of the beam that are bonded and you do mid-span debonding, you can exceed that 130 foot rule of thumb that Troy mentioned. So, okay. Reid, are you still on? Do you have any comments? Okay.
I was just going to make one comment going back to the concrete strengths. You can certainly assume something like an 8/10 of your 28-day strength for your initial design. But once you get an initial design, designers can then, I guess I can restart that. Designers can then back calculate what they need to have, because you have what the actual stress at release is, and you know what the limits are. So you simply back calculate it. And then you could rerun it to get the cambers right. So I would just make a recommendation on that. Anything else? Let's see. We need to move on to another item. Other fabrication questions. What about the 90-day rule? Any comments on that?
I know the answer to this one.
Well, I can answer a question that was also asked on the chat about the picture. Pictures of stability issues. Ever since I sent a dear good friend of mine a picture of a beam getting hit by a train, I've been having a hard time sending out pictures of other issues we've had, because I can't watch a presentation without seeing that picture. So thank you, JP. But that picture, I mean, the purpose of that picture that I sent it to JP was exactly this question about the 90 days. I mean, if we're delivering a beam that's required to be 90 days old and it gets hit by a train, I got to make another beam. And if without some extra analysis, I mean, does the contractor have to wait 90 more days to build his bridge? You know, it can be problematic. And, you know, I think JP's answer of just design simple span works for probably 95% of the bridges that we're building and designing. So we can avoid that 90 days with a little analysis, or like a couple extra strands or higher concrete strength. So it's, I mean, I'm not a proponent. I don't like the 90 days. I had a job that had a 180-day requirement.
Wow.
And that had issues as well. So
I think that's that's a good example of, lots of times as designers, we think more is better. So, more confinement steel. We only have to have it for 1.5H at the end, but we're going to run it for the full length. Or let's throw some
Right.
extra vertical steel in for crack control at the ends, or, or make the 90 days into 180. Those things that sound easy enough for us as designers can really cause problems in being able to fabricate and complete structures. So we just need to be careful that we don't think we're doing a good job and really end up breaking something else. Any other comments there on the 90-day? I might mention too, I was actually on the research project. I was a consultant to the research project that came up with the 90 days. It was suggested by a prominent state bridge engineer that 90 days might be a great idea to have. And it can be a good idea, but it is by no means written in stone. It was something to go beyond what we figured that the variation would be. So it can certainly be less than that, or even eliminated with proper detailing. Or if you go to the simple span, then you don't have to worry about it. Just make the decks continuous. So I would encourage people to recognize that that is not some kind of rule that came down from a mountaintop. It is just something that was intended to help us out, but has had unintended consequences.
Yeah, speaking as a designer, the making a beam continuous for live load, if you have those fixity moments caused by the cambering of the beams, they kind of work against your design as far as you're adding positive moment to the beam. So that's why we're saying design for simple spans, because the benefits of making something continuous for live load are they're there, but they're minor. So it's not going to affect your overall design much. So either making it jointless using, say, link slabs, that's something you could do, or just designing it positive for simple spans and just run the deck across the pier. It greatly simplifies the details, and it does not have that significant impact on the design of the bridge.
I would add just deflection, if it's a longer beam, could be affected by your continuous for live load design. So I think if you design it continuous for live load with reasonable stresses in your bottom fiber, if you turn around and check it for simple span, you should really allow yourself the knowledge that you will be behaving continuous. So if for example you just have a feel good about designing for compression under service 3 stresses, or you want to be near compression in your design, in a continuous system, sure, that's a good design and may well work, or minor stresses in the bottom fiber. When you go to simple span, when you're checking this condition, allow yourself to go to the thresholds that the Lrft or your local specification permit. I think that's important, because the actual behavior will be continuous.
Right. Good point.
Why don't we move to some topics about repair? I think that was something that we've seen some questions come in about repairs. And some of them are sort of tied in. I think we've responded to some of the repairs. One was about what are we talking about with missing and projected reinforcing steel. We covered that by an answer. It's typically bars at the ends that are either cut off or broken. Ways to avoid hairline web cracks in the ends of the girders caused by pre-stressing. We have provisions in the specs that are supposed to help us control those, but they don't eliminate them. You can't, it's reinforced concrete in that direction, and you have some really concentrated forces. So the cracks can occur, but typically will close up once the deck is put out there, installed.
But just add to that, Reid, I'd like to add one thing about the crack widths. The Astro Lrft provisions for serviceability, if you read the commentary of that provision in the Astro Lrft, it talks about what is an acceptable width of crack for even severe exposure. It's more than you think. If you have a crack that's less than 10,000ths of an inch, it is not considered a significant crack that we need to be worried about, even for severe exposure. So the repair guidelines that JP was talking about, and the ones that we have for the Northeast, are based on repair techniques that are based on those crack widths that are in Astro. So I've heard a venerable precast expert at one time say, if you think there's no cracks in the end of your beam, you're probably not looking for them, but they're very tight. They're tiny, tiny cracks, and they are not detrimental to the behavior, for the service behavior of the bridge. So we should not all freak out when we see a crack in a product. We have repair procedures, and if the cracks are small, there may not be any repair required. And that's what we try to cover in these documents, to make engineers aware that minor hairline cracks are not a cause for rejection of a piece.
Certainly not for rejection, and probably not requiring repair even.
Right.
So, yeah, that's something that is frequently an issue. We'll let the pre-stressors chime in on that. Any comments?
Yeah, one from Russell here at Penn Stress. Just one thing to note, when you do see a crack, I mean, I agree with everything you just talked about there, but one thing to note is, kind of make a judgment from what's going to happen to that crack also in the life of the beam. Is it going to be under compression? Is it going to be, where exactly is it at? Things like that. The epoxies and the injection that you can do to a crack, if it is required, I say are amazing. I mean, we, and as precasters, I'll go through videos and document it the whole way through of what can happen to heal, to seal, to completely inject that crack to the situation that it's going to be, what I say better than new. And the fact that, depending on where it's at, it may only ever see compression in the rest of its life, so to kind of take all that into account and as what was said earlier, don't be alarmed. It is concrete. You got concrete and you got steel and you got a lot of force on the strands, so to not have cracks is very abnormal, of some degree.
And many times the cracks may even be in an area that's encased in concrete. There may be small spalls that occur at the end of the beam, and that all ends up being encased in the concrete. And if we can just remove loose material and prepare the surface, it will be encased in its final condition.
Good point.
Yeah,
And again, I'll reiterate what I said before. The reinforcing we place in beam ends is crack control reinforcement. It's not crack prevention reinforcement. The reinforcement doesn't really do anything until the crack occurs, then it keeps the crack tight. So again, putting reinforcement at the end of the beam does not guarantee you're not going to get a crack. What it does guarantee is you're going to get a very small, very tight crack, which is what we're looking for.
Yeah, I'll add to that from experience. We had a job where the rebar details didn't necessarily match other regional details. We had cracks that exceeded the 0.001, and we modified the details to mimic standards that we were accustomed to, and the cracks were all then less than 0.01. So, they're still there, but they were manageable and they fell within the thresholds. So rebar detailing is super important in the ends. Weld wire mesh goes a long way as well, because you get that development of the wires, the vertical wires, and you get a lot of stiffness there at the end region.
One thing I might mention is we talk sometimes about welded wire or high strength rebar. When you are doing crack control, the higher strength doesn't really help you. I wouldn't reduce your areas of crack control reinforcement based on an increased strength. I would keep it at the same working stress that you have been using for grade 60 steel.
Yeah, excellent point.
Agreed.
How long do you all expect those repairs, if any, are required? Say it's maybe out in the span type of a repair like JP showed in some of his pictures. How long do you expect those to last? We had a question, I think, related to that.
I guess I'll pipe in first, because there was another chat box item there too. Our intent with the repairs is they're as good as the beam itself. So our intent is these repairs are good for the life of the structure. And our choice of repair methods is based on that. I have another question that came up about, should we be sealing cracks if a maintenance crew sees cracks in a beam? And you could go to our guidelines. Our guidelines are intended for plant fabrication and construction. They're not necessarily a service life for the rest of the bridge. However, you could apply a lot of our standard recommendations. If you have a crack below a certain crack width, certain repair procedures might be in order. In most cases, you don't need to seal a crack that you found during an inspection. Again, the width of the crack is critical. That's the key thing. So our guidelines do give recommendations. When a crack gets above a certain amount, we recommend a repair procedure, a certain width, I should say. That being said, the width of crack is important. So what happened in Florida, that pedestrian bridge, we can all agree, those cracks were well beyond what we would normally expect in a structure. So the key thing to all cracks during the service life of the structure is to look at the width of the crack and pick a repair procedure that's appropriate to the crack width.
Great. I think maybe seeing how we're getting low on time, how about if we go to UHPC? It would be interesting to hear from the producers what their thoughts are about UHPC.
Russell stepped in here from Prestressed. Yeah, we only see, great possibilities with UHPC, not just from a joint situation, but also from product member, decrease in section properties and getting more span out of it. And, so we see, great things in the future with UHPC.
Anyone
Okay,
else have a comment?
Yeah, this is Troy from NPP. We're verbally committed to working with Lehigh University and Penn State University on a UHPC research project. I think the scope is a little bit early at this time, but the idea is to help PennDOT get more comfortable with the product, so maybe we can use it for things, but it'll also help everybody nationally, just like when we did the same thing with SEC. So we're excited about it and wanting to get making things with it.
And from a designer's point of view, I think it has a potential to revolutionize our industry. This is we are working on a UHPC next beam. We're working with JP and Federal Highway to develop a section. We're looking to take about 45% of the weight out of the piece because next beams are heavy. So we're going to reduce the weight. And as far as pushing span lengths, what's going to probably control is deflection and span depth ratios are probably going to kick in as that's going to be the wall we're going to hit. But that's a great wall to hit. We can push these things out very far. And it really is a revolutionary product that I think the industry, what they have done is got the price of UHPC down such that we can mass produce it in plants. And that is a game changer.
Yeah, and I do want to say that we have brought it to the PCI Northeast Bridge Committee, and obviously currently we're working on updating the ABC guidelines. And what's been slated for our next project after we finish the ABC guidelines is to actually start working on UHPC. We're hoping that Federal Highway will have their design standards available by then. And we're thinking next beam might be the first project we work on. We've already got we've kind of roughed out what the next beam might look like if it's a UHPC girder. JP said he would test it or work with us.
No, JP said he would help fabricate it. Federal Highway has offered to test it. If we can build a beam, they'll test it for us.
Potentially would test it. So
anytime.
That may come quicker than we think. And we actually are also looking at potential other applications that we could potentially develop under our bridge committee for UHPC. And I think some of this might shake out starting next year. So it's going to be coming quicker than you think.
Yeah, we are confident we can build a next beam without any stem reinforcement at all, including at the ends, where the releases. We think we can come up with a section that has no reinforcing in the stem, which will dramatically, UHPC is an expensive material, but if we eliminate all the reinforcing in the stems, that's a lot of labor and a lot of steel that we're not putting in the beam. So I don't care if the UHPC costs 2 or 3 times more normal concrete. There's a lot of labor involved in putting steel in a beam. And if we can eliminate that steel, that's a huge advantage. So more to come. It's an exciting time.
Well, I think we're close to the end. I don't know if we want to wrap it up there. If Rita or Don, you want to jump in?
Yeah, I think we've answered a fair number of the questions. I did look at the QA chat pane, so there is still some questions that did not get answered, but I think what we will do, because it is 1:30 now, is we already have a running list from session 1 and 2. We will add all these questions to that list and have all those questions answered. Our goal is to have all the recordings of the 3 sessions available, along with the Q&A portion, the other resources that we also provided to you in the links to download. And once it's all available, we'll email all the attendees that have attended the seminar in case they do want to go back and view some of the recordings that they may have missed, or potentially they want to listen to it again. I'm not going to give you a time frame because it's going to take us a bit of time to get all of that done, but it will be available hopefully in the near future. Also do want to note that if you are looking for your continuing education credit, and Don did mention that at the very beginning, whoever attended today's session, this will be reported to PCI National. You will get a prompt from RCEP to download your certificate once PCI actually gets all that information posted into the system. Usually we say about 10 days, but PCI has been quick on the turnaround, but I would say that as a rule, it's 10 days. So you should get a notification. Check your spam box if you don't get it within 10 days to make sure it didn't end up in that location. Dawn, I think you're on too. We want to thank all our speakers for the Q&A today, and also the presentations, and basically for the other 2 sessions too. It turned out to be great. I think we had over 1,500 people total in the 3 sessions. So it's been a great turnout. I think I really want to thank all the speakers for a phenomenal job, and all the attendees for really being diligent and coming back. I did see, as I look at the participant pane, a lot of people that did come back and participate in all 3 sessions. So I will switch to Dawn to see if she has any additional closing remarks. And again, thanking all our speakers.
Yeah, thank you, Rita. And I will echo everything that was just said. It was a great effort for all of these speakers, everyone that participated. We really tried to answer all of your questions throughout, and we will make available your responses to these questions if we didn't get them. So all of the handouts, every single session, all the recordings, we'll make it available. And as Rita said, we'll make it available on email. We'll send you an email to let you know the landing page is up with all of these various resources and materials to you. And finally, in conclusion, we will send you a survey. We just want to hear from you. If there are topics that we didn't answer, that you would like further information from PCI, we'd love to hear that. If there are sessions you would like us to conduct individually with your firm, we're available to do that. Usually we do that jointly with a fabricator, because these kinds of practical questions come up, and we love to have them partner with us to answer your questions. So we'll look forward to that. So thank you, all of you, for your excellent feedback. We'll look forward to more of it from the survey if you choose to participate in that. And I want to conclude by thanking all of the speakers. You did a great job. We appreciate every one of you for all of your contributions to this seminar, the 3 series of this seminar. So thank you so much.
Thank you.
With that, we'll conclude. Thank you, everybody. Thank you for sticking around for a few extra minutes.
Yeah.
All right.
Thank you all very much.
All right. Thank you.
You.